Okay, so the last part of the chapter is kind of a continuation on what we hit on Thursday. We said on Thursday that we can do a lot of unique chemistry at the benzylic position on carbon, or on aromatic systems. And we said the benzylic position is always the carbon adjacent to the ring, right? And so if we want to brominate it, we can hit it with NBS. In fact, you can do NBS in excess and keep on brominating the benzylic position as long as you've got available protons or hydrogens, right? And then in addition to that, we said you can do oxidation of the benzylic position using chromic acid or potassium permanganate. However, in either case, you have to use a really, really strong oxidant because we're doing a 6-electron oxidation. So a gentle oxidant simply won't get the job done. In addition, I said that you can only do benzylic chemistry if you have benzylic protons, right? If you don't have a benzylic proton, you'll simply get no reaction at all. So let's take a look at an example here. And this example is going to be a bit more complicated. Okay, so we've got this big molecule. And what we're going to do is we're going to treat this with chromic acid. And my question is, what product will we get out? And you can assume that we have excess chromic acid around in solution, not just one equivalent. So I'll give you a minute to think about this and then check with your neighbor and see if you agree. All right, who thinks they got this one? Give me a thumbs up. All right, so first thing I always do is I try to identify my benzylic carbons. So let's zoom in on this and identify the benzylic positions. I've got a benzylic carbon right there with the red dot. I've got another one right there with the red dot. Is that it? Yes, absolutely. All right, then the next question I have for you is, will both of those benzylic positions react? Which one won't? Bottom one won't? Why? No protons. So let's make a note of that. So will not react because there are no protons. All right, the top one definitely will. All right, so then we can go ahead and we can start working on this and we can say, all right, that top benzylic position will become what? A carboxylic acid. All right, people always get hung up on this and they say, where did the other carbons go? Poof, they disappear, they're gone. So even if you've got 1,000,000 carbons coming off of that, they'll be lopped off and this will become a carboxylic acid. The other carbon down here, because it didn't have any protons, will not react. And is there anything else that can react in there? The alcohol. What will the alcohol turn into? Carboxylic acid. So this is one of those reactions that's somewhat versatile, right? We can not only oxidize primary alcohols to carboxylic acids, but we can also oxidize benzylic positions to carboxylic acids. So it's pretty powerful that way. Yep?
Do we have protective agents for benzylic positions?
So the question is, can you protect a benzylic position?
Do you protect those groups of alcohols?
Yes. However, our textbook doesn't really get into that. Oftentimes what you can purposely do is halogenate the benzylic position, do chemistry on your alcohols, then you can dehalogenate the benzylic position to restore it, right? Our textbook doesn't really get into that though, because our textbook doesn't even show how to do dehalogenation. Yeah, good question though. All right, so now let's take a look at this in terms of synthesis. All right, this is kind of feeding into reactions that we've already seen before. So let's kind of couple this into other chemistry that we know of. So we already said if you have toluene, you can react this with something like chromic acid or potassium permanganate. And then you can make this into benzoic acid. And then what else can we do with carboxylic acids at this point? Yeah, we can reduce them. So for example, we can do LAH and H2O to make this into an alcohol. So this would be benzyl alcohol, and then we can do reactions with alcohols from this. We saw in the alcohol chapter, we could take this alcohol, we could turn it into an aldehyde, we could turn it into a bromine, we could turn it into a chlorine, we could deprotonate it and make it into an ether. We can do a whole bunch of reactions with alcohols from this, right? So alcohol reactions. That really ties into the entire alcohol chapter that we've previously covered, right? Conversely, what we could do is deprotonate this. Make this a carboxylate salt. And then with the carboxylate salt, we can actually do SN2 chemistry, assuming we've got some sort of primary or methyl alkyl halide, where we can just hit the backside and kick that off, and we can do substitution. So there's a lot we can do starting out with the simple starting point. The problem we had before was without knowing that first step, we couldn't really do anything with toluene. We were entirely stuck there. This kind of opens up that reaction flowchart that we saw earlier this term. So you could, if you want, tether this in to that main overarching reaction flowchart. Does that make sense? All right. Conversely, like we saw, we could react this with NBS and heat. And if we do that, then we can install a really nice functional group. And then from here, we can do SN2 chemistry with some sort of strong nucleophile. Or, like we saw in our problem of the day, what else could we do? The Grignard reagent. So we can do substitution, or we could do a Grignard reaction. So really, this opens the door for us to a lot of new interesting chemistry. So don't be surprised if on this next exam, or if on your final exam, I tell you you have to start from toluene and then build certain molecules, because I want to see that you know how to incorporate this chemistry into the chemistry that we've covered all year. The other thing that we can do is we can work with more complicated systems. So let's say instead of having toluene, we have this starting material. My question for you is, how can we do alkene chemistry starting from this? We can't do alkene chemistry with the aromatic system. So how can we make an alkene from this? Does anybody have an idea? So we could use potassium terbutoxide, but the problem is we don't have a leaving group on there yet. Now we can add a leaving group. So now we can use MBS and heat. And then in this case, we've got a few options. We could do sodium hydroxide. Make an alkene, and then we could do all sorts of alkene chemistry as well. So that goes all the way back to the start of the term. My question, though, is why doesn't this do substitution chemistry? Yeah, why does it favor elimination over substitution, though? Hydroxide's a good nucleophile. Not quite. Think about the substrate. It's tertiary, right? A nucleophile is going to have a heck of a time doing SN2 chemistry there. Okay, so what if we absolutely wanted to do substitution and we didn't want to do elimination on this? And what I mean by that is how can we, let's say, get this all the way to an alcohol without running into the elimination product? What reagent would we need? Not quite. So if we don't want to do SN2 substitution, we've got another alternate, SN1, where we don't need a strong nucleophile. So in that case, we could get away with just using water and being really careful not to increase the temperature high enough to favor an E1 elimination reaction, right? And then from here, you can do alcohol chemistry. So really, this is tying into a bunch of reactions that we've already seen before and can be quite versatile. So I did want everybody to remember that. And then the cool thing with this is we can actually go from the alcohol to the alkene. How can we do that? So if we did PBr3, we could go backwards, right? And kind of work our way back, or we can get there in one shot. Could do catalytic acid and heat, right? So there's a bunch of different ways you can dance around these reaction charts. One thing I really want to recommend that you all do before the final exam is try to go back to your reaction map and fill in the gaps and holes and try to turn it into a cohesive map as a way of reviewing. Sometimes just going through and rewriting your map multiple times is a good way of seeing all the reactions that you might not necessarily use regularly. Does that make sense? All right. We have one last reaction, and then we're done. All right, the last reaction is the reduction of aromatic compounds. All right. And we've seen reduction chemistry a little bit before, but this is going to take it in a new direction. And the question I have first is what happens if you treat this with palladium on carbon and hydrogen at relatively low pressure? Is it going to reduce the aromatic ring system? No. It'll only reduce the alkene, right? And then if we really, really wanted to reduce the aromatic system, what we would have to do is amp this up, use 3 equivalents of hydrogen gas, a special nickel catalyst, and we would run this at about 100 ATM, which most labs are not at all equipped to do. Normally you have to have very specialized equipment to accomplish this, and then you could reduce the aromatic ring system. Yep?
Even at high pressure, would it work?
Usually not. Yeah, usually if you want to reduce an aromatic ring system, you have to go to a different catalyst. Yeah, that's a good question. So really, this last reaction is not super useful. It's normally something that's only done under weird circumstances where you're trying to study how aromatic a molecule is. So you could look at the enthalpy of the hydrogenation and study it from a physics point of view. It's not really synthetically used very often. However, there is another reaction that is used a lot more often, and this is called the Birch reduction. Yep.
Could you do that top reaction? Could you do one step by just throwing the palladium and carbon and nickel and increasing the pressure?
Yeah, if you wanted to go straight from point A to point B, all you would need to use is this last reagent and just really blast on it. It will reduce alkenes just as well as the aromatic ring. Yep, good question. All right, so the Birch reduction is a little bit different. In a Birch reduction, you have an aromatic ring system, and you reduce it, but you only reduce one of the pi bonds. So is this final product aromatic? No. Why not? Well, it doesn't follow Huckel's rule, but more importantly, these are now sp3 hybridized carbons. Right, so we've broken aromaticity. This requires a huge amount of activation energy to accomplish. However, it can be done with an alkali metal like sodium. Sometimes you see lithium used or potassium as well. It can be any alkali metal. And what does that little knot symbol mean in the top? it means it's elemental, it's not a cation, right? And then you need some sort of alcohol. I'm just going to abbreviate that ROH. It could be methanol, it could be ethanol, it could be terbutanol. Really, any alcohol will work here. And then last but not least, you need ammonia in order to accomplish this reduction scheme. All right, so let's see the mechanism for how this works. All right, so the first step involves the highly reactive metal, right? So in this case, we're just going to assume sodium, but like I said, it could be lithium or potassium. And sodium in its elemental state has 1 electron in its valence shell, right? That means it's incredibly unstable. What would the sodium really like to do? Get rid of that electron. So it's going to try to give up its electron to the most readily accessible source, which in this case will be the aromatic ring system. And because we're only moving 1 electron, we have to be careful with our arrows, right? So like I showed you before, if you're moving 1 electron, be really careful to only have a single-headed arrow, not a double-headed arrow. Okay, so it can dump it onto one of those carbons, but at that point, carbon's violated the octet rule, which is a problem. So instead, what we're going to do is break this pi bond, steal 1 electron and turn that into a lone pair on the top carbon. And then the other pi electron is going to get swung down there. However, that'll start to violate the octet rule, so it's going to steal an electron from this pi bond. And then last but not least, this other pi electron will hop down here. So it's a lot of arrows for this first step. But let's take a look at it. At this point, like I said, you'll have a lone pair on the top. You still have this pi bond on the left-hand side. You'll have a new pi bond on the right-hand side. And then down on the very bottom, what should be there? A radical. So this is going to be a radical anion because this carbon now has a negative charge, and sodium will be the countercation. It's kind of a cool intermediate. All right, and then in the next step, this is incredibly unstable due to the negative charge. However, you've got a proton source around. So this negative charge can really quickly do acid-base chemistry. We know acid-base chemistry is incredibly fast. And you can protonate that top position. However, we still have that radical position down below. However, normally this reaction is done with excess of your sodium metal. So at this point, your sodium can say, that's okay, I'm going to give a second electron to this position. That way we can pair up those electrons. Oops. And like we saw before, we have our protic solvent around, which is going to be our alcohol. So in this case, it can grab a proton off of our alcohol, and we can get to our final product. So one thing you have to watch out for this is sodium can also react with the alcohol solvent, right? We saw in our alcohol chapter, if you react an alcohol with sodium, it'll deprotonate the alcohol and generate hydrogen gas and give you an alkoxide. So if you have any electrophilic sites that can react with an alkoxide, you typically can't do the Birch reduction without protecting those groups first. Yep.
Why is ammonia used as a solvent?
That's a good question. Usually, I think it's to stabilize the radical anion. I'd have to look into that more, though. Yeah, that's a good question. All right, so now we need to look at this in more detail, specifically regarding the regioselectivity. So the question is, why did I give electrons to that top carbon and not any of the other carbons? So let's talk about that in a bit more detail. All right, and so let's take a look at this reaction. So in this one, we've got sodium, metal, and let's just use methanol and ammonia. The question is, which of these two products will we get? Will we get this product? Let me clean this up. Or will we get that product? What's the relationship between these two? Constitutional isomers. So now we've got to ask ourselves which one's more likely to be the desired product. And first thing I always like to do is I like to look at the carbon with our substituent attached, right? So if we look at that carbon is going to likely either react or not react, meaning it's either going to accept an electron or prefer not to accept an electron. And it really depends on the nature of the group coming off of it. So my question for this portion of the reaction is whether or not that group in green is electron withdrawing, or does it donate electrons to the ring system? So check with your neighbor and see if you can agree. All right, so let's check. Raise your hand if you think it's electron withdrawing. Raise your hand if you think it's electron donating. Raise your hand if you're not raising your hand. Ah, I got you. All right, so it's electron withdrawing. And one really easy way of telling whether or not something's electron withdrawing or electron donating is try to do resonance with it, right? There's no possible resonance drawing where you can push electrons from that group into the ring system. However, what you can do, for example, is you can say, well, there's a resonance structure where I could pull electrons out of the ring system onto the oxygen, therefore it's electron withdrawing, right? So we're going to spend a chunk of next term talking about this in more detail, but that's kind of our brief intro. So this is an electron withdrawing group, which tells us a lot about the nature of this carbon. Yep.
So does it not have to do with like electronegativity, whether it's withdrawing or?
No, it has to do with resonance, right? So if you have resonance structures where you pull electrons out of the ring system, that means the group's electron withdrawing. If you have resonance structures where you can push it in, then it must be electron donating. All right, so this, sorry.
Like electronegativity, like contribute a little bit.
A little bit. And we'll talk more about that next term. Yeah. We'll use relatively straightforward examples for right now. All right, so this carbon that I've highlighted in yellow, does that mean that it would like to gain or lose electrons? Gain, right? So it would prefer to gain electrons. So I'll just write wants electrons. All right, so knowing that, that means that that carbon would rather be reduced or oxidized. Reduced. So wants to be reduced. All right, looking at our two structures on the right, which one has a carbon in that position that was reduced? The first structure or the second structure? Oh, let's think about it. The second one, right? The second one gained a hydrogen in the process, therefore it was reduced. So over here we can say this one was reduced. Oop, shoot. Sorry about that. All right, so when we're looking at regioselectivity, this one over here is not observed. The one on the right is the observed product for this reaction. Does that make sense? So it's an easy predictor we can use to determine the reactivity. All right, let's take another example. What's this starting material called? Methoxybenzene or anisole. All right, so let's do the same thing with this starting material. We've got elemental sodium, we've got methanol, and we've got ammonia. All right, so now the question is, this group, the methoxy group, is that electron donating or withdrawing? So let's try both, right? So could we have a resonance structure where we pull pi bonds out of this ring system? Why not? Yeah, that oxygen would have more than an octet of electrons. That's not allowed. However, what we could do is try the opposite, and we could say, all right, what if we kick electrons all the way over to that carbon? Yeah, that works. So that methoxy group must be electron donating. Which again tells us a lot about the nature of this carbon right here. Does this carbon want to gain or lose electrons? Okay. Or another way of thinking about it is it can't really lose electrons very easily, as it does not want to gain electrons. So it's not that we're necessarily going to oxidize it, it's just that that position really doesn't want to be reduced. Okay, so again, we can go through and we can predict the two possible outcomes for this reaction. Let me clean this up. I don't like that ring. All right, which of these must be the appropriate product? The first one or the second one? Second one, right? Because this one had a carbon that was reduced right there. So this first one is not observed. The second product would be the major product for this reaction. Does that make sense? All right, so let's do a challenge one now. Okay. All right. So let's do a Birch reduction with this. And I want you to predict what the product will be for this reaction. Well, what we got to do is we got to analyze each of the substituents coming off, right? So let's just piecemeal this and focus on one at a time. Is this group going to be electron donating or withdrawing? Withdrawing. So I'm going to abbreviate that EWG for electron withdrawing group. Because the only resonance structures we can draw are resonance structures where we pull electrons out of the ring up to that oxygen. We can't do any electron pushing where we push electrons into the ring. All right, what about this one down here? It's donating, right? The lone pair on the nitrogen can be dumped into the ring system, so this would be an electron donating group. All right, and then last but not least, got this one right here, methyl group. Can we do resonance with the methyl group? No? Okay, so now we're kind of stuck in this pickle. The question is, well, do methyl groups stabilize positive charges or destabilize positive charges? So another way of thinking about it is when we ran into carbocations, we said that this is more stable than that, right? Why? Hyperconjugation, which means that even though those methyl groups aren't directly donating electrons to that positive charge, they're acting as kind of like electron donating groups to stabilize it through weak orbital overlap, right? So in this way, it's kind of similar to carbocations, where these alkyl groups are weak electron donating groups. All right, so I think we've got a really good start at this point. So now the question is, which carbon would very much like to be reduced? The one on the top, right? So at this point we can say the top one wants to be reduced. So let's go ahead and actually do this reaction mechanism. Whoops. And we'll show sodium donating its electron to this top carbon. I'm running out of room. Here we go. And then this pi bond will donate an electron, dump one over here. Pi bond will dump one over there, and then down there. And like we said, we can always identify the carbon that wants to be reduced because it's the carbon that has the electron withdrawing group attached. So now we've got an anion off this top position. We've got a radical down below. And then what's the next step in the mechanism? We need to protonate, right? Acid-base chemistry is super duper fast. So it will steal the proton from the more protic solvent, or more acidic solvent, I should say. Ammonia is not a very good proton donor. We have a radical now, and then what will happen to this intermediate? Sodium will donate a second electron. Some people will ask me, well, why doesn't sodium donate its second electron up above in the first intermediate? Does anybody know why? Acid base is faster. That and it would be a dianion, meaning having two negative charges on one molecule, which is incredibly unstable. So it would prefer to do this stepwise. Again, we regenerate our anion, and then what's the last step? Protonation one last time. All right, so this anion will reach over, grab this proton, and we would get to our final product. Does that make sense? So it's kind of a steppy mechanism. I will say the area that most students mess up is they forget to think about electron donating and withdrawing groups. And quite often in this first step, they get kind of lost with the arrows because there's a lot of arrows in that first step. So make sure you are tracing your electrons and using single-headed arrows. Yep.
What if there's two electron withdrawing groups?
Yeah, that's a good question. The question was, what if there's two electron withdrawing groups? It kind of depends, right? So if they're para to one another, then they both win, right? They're both reduced. However, if they're ortho or meta, you oftentimes have to determine which one's the stronger electron withdrawing group, which is something we'll cover first chapter next term. We haven't quite gotten there yet. But as far as we're concerned right now, I'm not going to try to trick you, at least not on purpose.
If you can't really break the tie, are you going to get like a mixture of...
Yeah, if it's a tie in terms of electron withdrawing groups, typically you get a mixture. Yep. All right, so that's where we'll stop today. Remember, tomorrow we'll be going over the practice exam. I also threw up a handful of practice problems in OneNote that are just pulled from the textbook. Good review problems if you want to look at those as well. I'll post the key later.